Good day, my name is Martin van der Merwe and I am the Director for Sustainability and Decarbonization in Asia Pacific with Emerson. In today's presentation, I'll share with you how Emerson's technology impacts hydrogen project success and share some proven results from projects that we've been involved with. Emerson is a global automation and software leader delivering solutions globally for over 130 years. Through our software control and intelligent device business groups, we've provided the broadest automation portfolio across all industrial and manufacturing segments in that time, including the evolving decarbonization segments such as hydrogen. A few years ago, Emerson acquired a controlling stake in AspenTech Technologies, and together we continue to innovate and develop software and control solutions to support the hydrogen industry. And I will present some of those synergy solutions today. So what does Emerson's portfolio consist of specifically, and how does it apply to the hydrogen value chain? Well, as mentioned, Emerson has one of the broadest automation portfolios in the industry, starting from the foundational layer with our smart instrumentation to measure process variables and valves to control those processes. The hydrogen industry specifically requires accurate, traceable, and safe instruments for hydrogen production, storage, and transportation applications. This forms part of what we call the intelligent field. The instrumentation provides data into our control and safety systems, and with applications for advanced control, asset management, SIL3 capable safety systems, and edge devices, this control layer serves data securely into the enterprise layer, where our powerful analytics, software and process optimization, predictive maintenance, energy management systems all reside. As the hydrogen sector continues to evolve, we continue to innovate our solutions to solve the challenges of this growing industry. Some examples of that include the development of our high pressure and liquid hydrogen Coriolis flow meters, liquid hydrogen isolation valves, including the pressure release devices, for which we recently received the Preliminary Innovation Award at the H2 Meet conference. Of course, one of the key challenges for hydrogen projects is driving down project costs. And while automation typically only presents 2 to 3% of CapEx investment, taking advantage of the capabilities that automation provides can save a project in excess of 30% in construction and engineering CapEx investment. This is achieved primarily through savings in infrastructure costs and reduced engineering effort and risk. The intelligent field with wireless instrumentation and streamlined connectivity reduces the need for a significant amount of structural engineering, cabling, and testing. Containerized software and control applications at the edge reduces the equipment required, such as server and control panels, which minimizes the required footprint, power, HVAC, and so on, while securely serving up data into the enterprise cloud, where these contextualized data sources can be easily accessed by the correct business department for engineering, maintenance, safety, and business management. So this is what we call boundless automation. So it becomes a bit more critical then than ever to engage and evaluate your automation technology partner very early. This traditionally only occurred after FEED, but that limits the ability to maximize project cost savings that I mentioned before. So we see projects that consider the automation impact at feasibility stage or even at pre-feasibility being able to take advantage of these opportunity savings. In order to improve the viability of the hydrogen sector, scalability and size will be critical. Many green hydrogen projects start small as 1 to 5 megawatt pilot projects, often using non-industrial simulation applications and PLCs. These projects typically aim to demonstrate and evaluate the performance of the hydrogen application. From there, we see the first phases of projects in the range of tens of megawatts, implementing modularized industrial automation technology. Many of these projects have future phases to scale into the hundreds of megawatts. And as these project sizes increase, so too does the complexity in the requirements on safety design, the efficiency, maintainability of the equipment, and even remote and autonomous operations. We see on these scale projects that PLCs typically on electrolyzer skids are no longer fit for purpose. They become a bottleneck for effective data flow and efficient operations and management. And so the importance of front-end digital twins and the deployment of fit-for-purpose automation with easy access to data from the field devices play a much more important role to minimize the capex of these projects. So that is the concept, but let me give you a real-world example to explain how that works. A customer has developed an integrated green hydrogen production and storage plant concept. They engaged Emerson early and learned about AspenTech's Fidelis solution that allowed them to run Monte Carlo simulations of their energy sources, electrolyzer efficiencies and stack configurations, storage capacities, and offtake schedules. They ran multiple what-if lifecycle scenarios in Fidelis to validate the feasibility of their project. And using this software, they then further developed detailed process models using Aspen Plus and concurrently used the HYSYS models from their selected electrolyzer supplier to create a high-fidelity hybrid process digital twin, together with AspenTech's AI-optimized 3D OptiPlant design. Using the process data, they specified equipment and optimized the CapEx cost using AspenTech's capital cost estimator tool. Because they engaged us early, they were able to identify with this capital cost estimator tool that the architectural benefits of Emerson's electronic marshalling with distributed charm I/O and wireless instrumentation not only simplified the design, but saved them in the order of 30% in construction costs. As front-end engineering and design commenced on this project, they used the same hybrid process digital twin and interfaced it with Emerson's Mimic simulation software. This software simulated field values from the process model and presented it to Emerson's cloud-based DCS simulated automation digital twin, where all the control strategies, the HMI, the alarming, ramping sequences for the electrolyzers and energy management of the hydrogen plant was simulated and optimized. Emerson's technology is focused on the fit-for-purpose nature of hydrogen projects, as I said before, and we eagerly participate in many of those smaller scale innovation projects. I've summarized a few international projects like Neptune's Poseidon project that uses offshore platforms in the North Sea, converting them to green hydrogen production stations that blend hydrogen into the existing gas infrastructure. We also support new electrolyzer and fuel cell technology developers, such as Cavendish's AEM and capillary technologies. And we also have significant engagement in many hydrogen mobility solutions with H2Korea and Biotech, SoCalGas, and here in Korea with Cohygen and most recently HyIS. But our technology also plays a critical role in the integrated systems required for hydrogen production. We've been involved in hydrogen production projects for a long time, since the Air Liquide site in Canada was commissioned. And we have gained significant experience in our engineering and support teams as we continue to implement projects across the many regions that we serve. There's not enough time to go through all of these references, but I'll dive into a bit more detail on the Mitsubishi Chevron Advanced Clean Energy Storage, or ACES, hub project. just to illustrate the scaled complexity of this 220 megawatt green hydrogen project. The aim of the project is effectively to a combined cycle peaking power plant using clean hydrogen produced from excess renewables and then stored into two massive underground salt caverns capable of storing more than 300 gigawatt hours of hydrogen energy. When the electricity demand is high and the pricing is favorable, the hydrogen is used to run an 840 megawatt hydrogen-capable Mitsubishi turbine using hydrogen from the stored salt caverns. This project selected Emerson's technology for the entire automation scope, from DCS, the safety system, the PLCs, asset management systems, field instrumentation, and valves. To highlight the complexity found in this project, which is one of the largest green hydrogen production projects under construction currently, I'll run you through the architecture and design concept. The project uses 45.5 megawatt Hydrogen Pro electrolyzers that are configured into 20 trains of 11 megawatts each. Having this many electrolyzers and variable energy supply presents quite an interesting and complex control challenge. We firstly need to consider the state-based operation of each electrolyzer that's represented and illustrated here in the top left. In our automation platform, we have simplified the configuration complexity of such state-based systems into function blocks that are easy to understand, configure, and fault find. Secondly, we needed to develop algorithms to prioritize and optimize the electrolyzer train starting sequences based on the power demand set point from the energy management system. Now, you don't want to develop and test this for the first time on the physical equipment. So the project used extensive modeling processes and automation digital twin deployments, as I shared earlier, to develop these test algorithms and implement them in the virtual space in these digital twins prior to implementing them on the equipment, which is currently being commissioned. So I hope that gives you a bit of a flavor of the complexity of larger scale projects that Emerson is involved in. So to summarize, ensure that you engage, identify, and leverage your automation technology partner early in the development of your hydrogen project so that you can take advantage of boundless automation with process and automation digital twins that will deliver market advantage through investment certainty, lower capex cost, lower operational costs, operations optimized to reduce OPEX over the planned life cycle of the facility. So if you found this interesting and you'd like to connect with our team, please visit our booth and also be sure to join our Chief Sustainability Officer, Mike Train, during the panel discussions later in the week. Thank you very much.